Hey guys, welcome back to Notes with Griff. This is our last section from Chapter 6, so that should be exciting for you. Alright, Chapter 6 talks about enthalpies of reaction and standard enthalpies of formation. So as I said in video 6.8, we were going to continue talking about Hess's law and delta H. That is a true statement, except now we're going to get something called standard enthalpies. So let's just jump right in. Standard states and standard enthalpy changes. So the reason we have standards, whether it be a kilometer or even standard temperatures and states, is so everybody knows what we're talking about, and then that way we don't have to question where did this reaction take place and so on. So let's just jump right in. In chemistry, we have standard states. For a gas, the standard state is 1 atm. 1 atm most of the time is atmospheric pressure. All right, and this is actually atmospheric pressure at sea level, but 1 atm is really close. For a solid or a liquid, we're talking about a pure substance in its most standard or stable form at 1 atm and a temperature of interest. Most of the time, except for gas laws, we're going to be talking about 25 degrees C, which is room temperature. So that's why we use the temperature of 25 degrees C, because that's room temp, and so we don't have to cool down our laboratories to do our experiments to get the same results as someone else. And last but not least, if we have a substance in solution, those concentrations are 1 molar. And remember, 1 molar means 1 mole of the substance is dissolved per liter of solution. So when we talk about standard, anytime we have standard state, we're going to label with this little degree sign. That lets every scientist know that we are at standard state. And when we have a standard enthalpy change, we're talking about all reactants in our products in standard state. So we're talking about them being all our reactants and products are at 1 atm and room temperature, which most of the time is just like a regular chemistry lab, which helps us because that way we know we're all at the same spot. The third thing there, that since we have standard enthalpy change, we can also talk about enthalpy of formation. And that's exactly as it sounds. Notice how we've added the little f. But formation talks about how much heat it took to form that substance. So, for a pure compound, it's the change in the enthalpy when 1 mole... This is a key. When 1 mole of a compound forms from its elements in their standard states. And we're going to talk about the pure elements in just a second here. So we're talking about 1 mole of a compound forming from its elements in its standard state. So that's going to tell us how much heat it took to, let's say, make carbon dioxide from carbon and oxygen in their standard states. And the reason that that is effective or useful is if we look at a pure element, such as carbon or oxygen in their natural states, so carbon as graphite and oxygen as gas in the air or as O2, delta H of formation is 0. What? Does that make sense? Take a couple of seconds and see if you can explain that. I will explain it in just a couple of seconds. So why is the heat of formation for an element 0? Well, does it take any energy to form oxygen? Right? Oxygen gas is just existing in the air right now, and most of our elements we can find when we find them naturally, they are in their most stable environment, right? Graphite in our pencil is carbon, and that didn't take any energy to form, so that's why we're talking about it that way, and it didn't take any energy. It didn't take any energy, it didn't use any energy, it's just naturally there. So they set delta H naught F for 0 for those elements, and everything is kind of based off of that. So let's move on just a little bit here. Keys for standard heat of formation. The elements must be in their most stable form, and only 1 mole of product must be formed. So if we look there, Write equations for the formation of MgCO3 and C6H12O6 from their representative elements in their standard states. Include the value of delta H not F for each equation. So what we're trying to do is we're forming 1 mole of MgCO3 solid, and it's got to come from its elements. Obviously, I wrote this a little too close to the side here, so let me slide it over just a little bit. So, the elements that make it up, Mg, C, and O. So, let's check this out. We've got 1 Mg, 1 Mg. Mg in its natural state, if you look at the periodic table, Mg is solid at room temperature, and C is also solid at room temperature, but we have to specify. There's a couple of different solids of carbon at room temperature, so we're going to say solid and graphite, because graphite is the most stable form of carbon at room temperature. And then we're going to say plus O2, and that's gaseous at room temperature, and that's going to get us our MgCO3, which is solid. Unfortunately, we are not done. We have to do a little extra work here, and we have to balance this equation. I'm going to give you a couple of seconds, but what I want you to remember is you can only have 1 mole of product, so fractions might be something we use here. I will be right back as soon as you're done balancing, and we will balance together. All right, that didn't take you very long to balance, so let's check it out. Or did it? Are you still balancing? So if we go and just balance it in terms of whole numbers, and then maybe we can get it back to fractions, because here's our problem. We've got 2 O2s here and 3 there. That makes it a little hard to balance with everything else. So if we check this out, that gives us 6, but that gives us 2 here and 2 there, right? But this can only be 1, so we have to adjust that in a manner that's 1. So how can we get that back down by 1? We can divide everything by 2 and make some fractions. So 2 divided by 2 is 1, 2 divided by 2 is 1, 3 divided by 2 is 3 halves, and then 2 divided by 2 is also 1. So this is actually how it is written. And so delta H of formation, this you can find in the back of your book, and I'm going to let you fill that in. And you're going to look in the appendix in the back of the book, or, well, since we're an online book, you're just going to look at that, find the appendices, and find delta H of formation of MgCO3. Make sure you're getting the solid, not the aqueous version. All right, let's repeat the same example for forming C6H12O6. So again, we're going to put C6H12O6 here, and it's a solid. And again, I'm going to let you look up the delta H of formations there. And so again, our substances that make it up, carbon, and that's solid in the form of graphite. We've got hydrogen, which is going to be H2, and that's a gas in its most stable form. And then we've got O2 again, also gaseous. And so now we've got a balance. Remember, this has got to stay 1. This one's a little easier. We're going to say 6 carbons, 6 H2s, and 3 O2s form 1 mole of C6H12O6. And again, you can find delta H of